Hi everybody, it's Jakub here, and today we'll talk about some combinatorial games, as they are called. So basically, these are games where usually there are only two players, and they are not really fun games to play, I would say. I mean, they might be fun, but the point is that we're going to prove that the first or the second players will always win in most of those games. And if you have a game where one person will always win, that maybe that game isn't the funnest game to play with your friends. Because, well, you can then either win or lose, right? However, it's not always obvious how to do that. So maybe there is some value in playing those games at some point, or maybe there isn't, but it's not the point. Okay, so let's just start from the simplest example that we have. We have the first example, and today we'll have some chocolate bites on a plate. Doesn't really matter what it is, a pile of stuff. And the rules are you can only take 1, 2, or 3 things from that pile, right? So let's first establish that the number of bites that are left on the plate at any given moment is the state of the game. What that means is that we're going to consider the state of the game as sort of telling you what you should do. Like in this state of the game, you do this. In the other state of the game, you do this. And we want to like fully describe the state. But in this case, we only need to know how many bytes are on the plate. Doesn't matter what other things are, like which bytes, you don't really, or who's in charge at the moment. And we will be talking about winning and losing position. As described in the introduction to this problem set, a winning position is a position from which you can win. You can win, so that means you do something and you bring your opponents to be in the losing position. Now, the losing position is the position in which you cannot win. So doesn't matter what you do, you will always end up losing, right? So what happens is that if you're playing and you're in the winning position, you make your move, and now the game is in the losing position, but now that your opponent is making their move, so they are in the losing position. And if you play smart, it's going to be winning, losing, winning, losing, winning, losing, and that's what we are talking about now, right? So let's say, first note is that 0, obviously if there is nothing on the plate, and you're getting a plate that has nothing on it, you're in a losing position because you've already lost. You cannot do anything, right? And in such a way, 1, 2, or 3 bytes that are left on the plane are winning positions, because if I'm given a plate and only has 1, 2, and 3 on it, then I can take 1, take 2, or take 3 and win immediately, right? So 1, 2, or 3 bytes on the plate are positions from which you can win immediately, right? So this is because we can win immediately, right? So this is simple. A winning position, the one from which you can win immediately. Easy. Now, 4 by plate is a losing position, and it's not obvious maybe at the first glance why, but because you're not yet lost if there's 4 bytes and you're given the plate. But the thing is, whatever you do, if you take 1, then there are 3 left, right? If you take 1, 3 left. If you take 2, there are 2 left, and 3, there is 1 left. I can't write R for some reason, right? And that brings us to the other player winning immediately. So it doesn't matter what you do, if you are given 4 bytes on the plate, whatever you do, your opponent will always win in the next move. So that's why we say it's a losing position, right? And that brings us to any plate with number of bytes divisible by 4 is losing, and any other plate is winning. Why that is? Because if I have a plate divisible, number of bytes divisible by 4, then I can take 1, 2, 3, and that gives my opponent the plate with something that isn't divisible by 4. So they can just always make it divisible by 4, right? So in the same way, if I take 1, there are 3 left above some multiple of 4, so my opponent takes 3. If I take 2, my opponent takes 2. If I take 3, my opponent takes 1. So then I get back a plate with 4, right? Let's go and talk about the actual game with our characters that we have. So first, explicitly, because we have 18 at the beginning, right? We had 18 at the beginning, I think. 18, right? It's okay to take 2 bytes and get 16, right? So now it's divisible by 4, right? 16 is 4 times 4, right? And if Andy takes 1, then Katie will take 3. If Andy takes 2, then Katie takes 2, and Andy takes 3, then Katie takes 1. So either way, then Andy gets a plate with 12 bytes, which is again 4 times 3. And if this continues, he just loses, because then you know, then this just happens again, and he gets 8, right? And then this just happens again, and he gets 4, and with 4 we know that he lost, right? So Andy keeps getting 12, 8, 4, and 0. And ultimately, Katie takes the last byte and she wins, and Andy loses. Okay, so that's the first example. And this is sort of a principle of winning and losing position. I know that can be solved in a much simpler words, just, you know, finding this explicitly that you need to do. But the idea that you sort of might learn from this set is that a winning position is the one from you can bring your opponent to the losing position. You don't have to. You can only do it if you know what you're doing. If you pick the right move and you're in a winning position, then you bring your opponent to losing position. But if you pick the wrong move, then you might not be able to do it. But in a losing position, you don't have a choice. Whatever move you make, you're bringing your opponent to a winning position. So that is the difference. So maybe let's hope you now have a better idea how to use this principle in the different problems, right? See you in the next example.